In the sciences, it's very common for people to do joint presentations. In fact, some groups are as large as 9 giving presentations. So we were glad to be able to share this with you. We're a tag team. I'm Jean Boyce, and this is Linda Glenn. And I thought we'd just tell you who we are.
Oh, yeah, well, it speaks for itself. I'm Professor at Alden March. I've spoken to some of the, there's a number of people in the audience who I've spoken with before, and our presentation will try and cover some new material rather than reiterate material that was previously covered.
Okay, I'm Jean Boyce, and I'm a professor of computer science, which puts me a bit of a fish out of water here. But I also am a roboticist and an AI person. But I actually did develop the first ethics course in the information age at the University of Maryland and at Montgomery College, where I currently teach. So I couldn't help thinking about the film, the old Twilight Zone, The Eye of the Beholder, in our morning presentation. We've seen it, the idea of defining beauty. A young woman who'd gone through many surgeries to become beautiful. And so that was one of the bases for our title. I thought it would be useful to go and give you a definition of what regenerative medicine and tissue engineering is defined as by the NIH, because sometimes it's better to ground in something that already has been determined. Their definition, and they have interchanged tissue engineering and regenerative medicine as one thing, as an emerging multidisciplinary field that includes biology, medicine, and engineering, is likely to revolutionize the way we look at health. And the purpose here is to restore, maintain, or enhance tissue and organ function. Tissue engineering is a fairly new field. It's been around for a bit. But it can have diagnostic implications, and it can be used for in vitro testing, drug metabolism, uptake, toxicity, pathogenicity. It allows the ability to exploit living cells. Living cells can be created into biomaterials, where you can merge technology with biological cells, and use chemical cues to cause it to behave in a certain way. We can just change cells, create exogenetic cells, stem cells, engineering cells, and this is another version of tissue engineering. We can create biomolecules, including angiogenic factors, growth factors, differentiation factors. We'll have everyone over 6 feet tall. Engineering design aspects are really a hot topic today in nanotechnology and machine design, in which we're including 2D cell expansion and 3D tissue growth, bioreactors, vascularization, cell and tissue storage, and biological packaging. There are biomechanical aspects, and as a person who works with the Society of Manufacturing Engineers, we are always discussing the impact of taking biological material and turning it into computing. We are now able to ionize and polarize DNA, so we can actually build computers on your own cell structure, using your nerve structure to generate the electricity necessary. So you'll have your own virtual private network that will be impervious to computer viruses because it will be your own body. Informatics, of course, is an area to support tissue engineering, gene and protein sequencing, gene expression analysis, protein expression, and so forth. And I assume you're getting copies of these, so I'm going to read them all to you. Stem cell research, it does fall under this category, but it has been very narrowly defined. You can involve tissue engineering using stem cells that are both embryonic, fetal, adult sources, human and non-human, but they are only to be used for developing tissue therapies, studying cellular differentiation, and research that will help you development studies. It does not mean transgenic studies. It does not mean the development of chimeras. So NIH has been very clear in limiting the use of the stem cell research. Now, Tissue engineering may be a term you're not quite as familiar with. They were four brothers from Boston, all medical people, who were walking along the beach one day and were studying seaweed. And they said, isn't it interesting the way seaweed grows on a single stalk with these little pods? And they wondered if we could create cell structures based on the idea of how seaweed grows, which is a stalk, a scaffold, in a nutrient solution. Dr. Oz was seen the other day on TV of putting magic dust on someone's finger to regrow it. It was a very popular view of tissue engineering on Oprah. But basically, you're molding cells around a basic biodegradable polymer, so that there has been tremendous success in regrowing ears and other body parts, including pancreases, and a friend of mine has been having her discs replaced. They've taken spinal discs, growing them externally, and will be putting them back into her body. So it's going on in Washington quite a bit. The Pittsburgh Tissue Engineering Institute is one of the key places, called the McGowan Institute on Regenerative Medicine. There are also cellular therapeutics, and in the NanoWork issue of March 29, it hasn't come out yet, just tomorrow, but it just came out. There is a new technique that they've been able to design by performing cell patterning using external magnetic forces, which will control the development of a cell along a substrata, and thus creating a 3D multicellular assembly to guide cell adhesion. What that really means is that we'll be able to generate cell motion using magnetic force. So if you ever want to go to the site, it's free to register at thetissueengineering.net, and you can get access to all the latest publication. It's a really wonderful site. A new development that has come up recently is the development of nanofluidic chips. The idea here is to develop a $100 genome analyzer. I was not aware that DNA actually has a tendency to curl itself into a little ball, making it extremely difficult to parse it and diagnose pieces of the genome. So what happens is they take a snippet, analyze it, they take another snippet, and then they sort of have to patch the whole thing together. Well, by using the nanofluidic chips, it's two magnetic fields, and they pass the DNA through it, which actually straightens it out. And they're able to potentially read the whole human genome in less than 8 hours, which has amazing potential for diagnostic and genetic profiling to help cure problems, save problems. They can then snippet 1 million DNA molecules from a piece at a time, which is a significant improvement of where we are today. The company that is doing this is called Nanomedicine Corporation, in case you wanted to follow up on that. This opens up tremendous possibilities for genetic engineering that we have not had before, using a biomechanical device. There's a new field called Nanopetronics. I thought if you haven't been exposed to it, this is a good time to introduce you to a new word. And this is the concept of using nanowires to power medical devices and serve as tiny sensors. Zinc oxide bends when it is formed into a nanowire, and it can actually create electric current from vibrations around it, which means that it can pick up the sound in this room and create an electric current, thus not requiring a power supply. The implications for this is the ability to do implants and other biomedical devices. One of the ones that is currently being investigated is the use of putting this implant into the knee to check on your stress level. If anyone who's had knee surgery knows that this is an issue. This sensor would then be able to diagnose the amount of stress going on the knee. And another concept here is the idea of creating hearing aids without batteries, because the ambient sound would create enough current to generate the electricity to run it. And anyone who's had people with hearing aids know they're constantly changing the batteries because they